Hello everyone, I'm Yazan Ibrahim, or as some of you might know me, Yazan Abu Ghosh. Today we're going to dive into a fascinating and essential topic from Chapter 4, Part A, Information Systems Operations, 4.7 Systems Performance Management. If you are a seasoned auditor or just curious to understand how information systems into business environments, you've come to the right place. Let's begin. Deep dive into systems performance management. When we think of a high-performing organization, we often conjure images of efficiency, speed, and seamless operations. But behind the scenes, an essential question lurks. How is all this achieved? The answer lies in a less visible area that drives everything forward: systems performance management. At its core, systems performance is about understanding how an enterprise's technological systems, hardware, software, and the connections between them function as a cohesive whole. Think of it as the lifeline for every digital operation, ensuring that systems work as expected and that issues are swiftly addressed. But to truly appreciate systems performance management, let's peel back the layers of how such systems are structured and function, starting with the heart of every modern computer, IS architecture. 1. IS architecture and software, the inner workings of a computer system. Every computer system operates on a carefully orchestrated hierarchy, a kind of digital ecosystem designed to work in harmony. At the very base of this structure is the hardware. Imagine it as the foundation of a skyscraper, made up of physical components and even embedded instructions known as firmware. Now, if hardware is the foundation, then the next layer acts as the control center, the nucleus, also called the kernel. This tiny, often overlooked component is like the air traffic controller of the digital world. Here you'll find processes like interrupt handling, process creation and destruction, and memory management, all activities that ensure the computer's operational flow remains smooth, but the kernel's capabilities are carefully guarded. Access to this area is highly restricted. After all, a breach here could disrupt the entire system. Above the kernel, we venture into the world of OS processes, the domain of system software. System software enables computers to perform the day-to-day functions we often take for granted. These tools play an indispensable role in tasks like controlling user access, managing databases, and scheduling jobs. Examples include network management software and job scheduling utilities. But here's the kicker. All this software must be compatible with the computer's operating system, OS. 2. Unpacking operating systems, the power beneath the surface. Now let's zoom in on the OS itself, the most vital system software there is. Not only is it the bridge between users, processors, and applications, but it's the governing entity that schedules operations, distributes resources, and oversees traffic like a city's busiest intersection. Modern operating systems have come a long way, evolving beyond mere file cataloging and program management. For instance, today's OSs leverage virtual memory storage techniques to bridge the gap between smaller, faster working memories, like cache, and slower, larger ones, like disk drives. But the capabilities of an OS aren't universal across devices, as different environments call for tailored systems. Take these scenarios. Imagine a powerful IBM mainframe designed to handle millions of transactions per second. Its operating system, like z/OS, handles extensive resource management and meticulous multitasking with laser-sharp reliability, essential for mission-critical environments. On the other end of the spectrum, consider a single-user PC operating in a small office network. Here, the demands on an OS may be more localized, prioritizing efficient file sharing, resource allocation, and ease of setup. No two operating environments are alike, which is why the tools and processes embedded in each OS must differ. And increasingly, those tools are built with an eye on virtualization, the ability to run multiple independent virtual environments on a single physical server. But even as operating systems enable flexibility and power, their complexity opens new doors to risks. From logging activities to configuring settings, every OS must maintain tight control over its operations, ensuring that data integrity, security, and permissions are firmly established. 3. The gatekeepers, access control software. Speaking of security, let's pause to discuss the unsung heroes of every system, access control software. This is what shields sensitive data and prevents unauthorized tampering. Whether safeguarding privileged instructions in a mainframe environment or monitoring remote access in a client server system, these tools ensure that only the right people operate within the right boundaries, but access control isn't just about barriers. It also watches for irregularities and attempts to bypass restrictions. IS management must consistently enforce least privilege principles, where each user or process receives just enough access to perform their assigned tasks. It's like issuing keys to a building. You wouldn't give everyone a master key that opens all the doors. 4. Ensuring software integrity, the foundation of trust. For a system to perform optimally, it's not enough to have robust architecture or access controls. The integrity of the operating system itself must be airtight. Hardware and software must work together to block deliberate modification and prevent processes from interfering with one another. Without such safeguards, rogue programs could freeze critical operations or corrupt entire databases. Consider the ZEOS system again. When it's first initialized, specific parameters are loaded from directories like cis1.palmlib, essential instructions that dictate how the system behaves. If these parameters are altered or left unchecked, it could spell disaster. The same scrutiny applies to modern systems like Windows or Linux, whose registries and kernel configurations house sensitive data critical to the OS. That's why activity logging is so vital. These logs capture everything from database queries to security updates, offering a traceable record of what happens within the system. But it's not just about logging, it's about protecting those logs too. Cyber intruders often target logs, attempting to alter them to cover up breaches. By analyzing secure, centralized logs, systems can maintain compliance and track anomalies effectively. 5. The role of data communication software. Lastly, let's not forget about the unsung backbone of connectivity, data communication software. Whether transmitting an email across countries or handling bank transactions in real time, this software ensures accurate, seamless data transfer across local and wide area networks, LANs and WANs. Such systems may seem straightforward, data flows from one point to another. But underneath lies a web of layers, from the physical hardware connections to the data link layer. These layers coordinate to bridge communication gaps, ensuring that requests, like a database query, are sent and received without error. This is especially crucial in high-stakes industries like EFT, electronic funds transfer, where even the smallest disruption could ripple outward. Bringing it all together systems. Performance management isn't just an exercise in technology, it's a delicate balance of architecture, processes, security, and communication. Each layer serves a purpose, and each tool is designed to keep things running smoothly. As organizations grow more dependent on technology, understanding these layers isn't just a technical necessity, it's a strategic advantage. Whether securing an IBM mainframe or auditing the network of a distributed system, knowing how these pieces fit together ensures that enterprises remain resilient, adaptable, and secure in the face of growing complexity. When we talk about technology systems, their efficiency doesn't magically happen on its own. Behind the scenes, specific strategies and tools work tirelessly to ensure these systems function optimally. Imagine a backstage crew managing everything from maintenance routines to planning resources and adhering to legal agreements. Each actor in this hidden story plays a unique role, from software tools that keep systems healthy to management practices that ensure fair use of technology. Let's break down these concepts into their core components, starting with some indispensable tools known as utility programs. Utility programs, the backbone of system maintenance. Utility programs are like the Swiss Army knives of computing, small but essential tools designed to carry out routine operations and maintenance tasks. They are carefully crafted pieces of system software that swoop in when your operations need support or analysis. Picture them as tireless assistants that monitor, clean, analyze, and even troubleshoot the system. Now, utility programs serve different purposes, and we can categorize them across 5 functional areas. Let's explore. 1. Understanding application systems. Have you ever wondered how a busy airport control tower keeps track of hundreds of flights simultaneously? That's essentially what flowcharting software, transaction profile analyzers, executive path analyzers, and data dictionaries do for our technology systems. They dissect applications to show us the big picture, helping teams understand complex programs from start to finish. 2. Assessing or testing data quality. Think of data as the lifeblood of any organization. To keep it healthy, tools like data manipulation utilities, database dump utilities, and data comparison utilities act as doctors. They analyze and test the quality of data, ensuring it remains clean, accurate, and usable. Query facilities, meanwhile, allow us to interact with data quickly and make sense of it. 3. Testing a program's functionality and integrity. Imagine assembling a puzzle. Every piece has to fit perfectly, right? Testing utilities like test data generators, online debugging tools, output analyzers, and network simulators make sure that every piece of a program fits both functionally and securely. They catch errors and ensure the system holds together under pressure. 4. Accelerating program development, developers often need tailored tools to speed up their work. Visual display utilities, text editors, code and report generators, and online coding platforms are the power tools of modern programming. They save time and boost efficiency, allowing developers to focus on innovation. 5. Improving operational efficiency. Finally, utilities take efficiency to the next level by monitoring crucial components like processors and communication lines. CPU utilization monitors and communication line analyzers ensure that nothing goes to waste and systems stay streamlined. Utility programs on smaller systems. The unsung heroes of personal computers and smaller servers are their utility programs. On personal devices, these utilities clean your cluttered virtual desk, verify the integrity of your data storage, or even restore files you thought you'd lost forever. For instance, tasks like defragmenting hard disks or testing system peripherals are managed by such utilities. However, there's a catch. Because these tools are so powerful, they can sometimes operate outside security systems and leave no audit trail. Without strict controls, they could become vulnerabilities themselves. Limiting access to these utilities is crucial to maintain security. 6. Software licensing, a legal and ethical frontier. Imagine someone borrowing your prized invention, tweaking it, copying it, and selling it as their own. This is where software licensing comes into play. It establishes the rules about who can use a program, how, and under what conditions. Every piece of software is essentially a contract between the creator, owner, and the user. Now let's take a closer look at the two main types of software licenses, free and paid. Types of free software licensing. Open source. This is the golden ticket of software flexibility. You get access to the program, its source code, and permission to modify and redistribute it. It's like being handed the blueprints for a machine and given free rein to build and innovate. Popular examples include Linux, which powers everything from supercomputers to mobile devices. Freeware. Freeware doesn't provide the blueprints but gives users full access to the software itself without cost. For instance, think of Adobe Acrobat Reader R. Widely used, but closed to modification. Shareware. Shareware is a try before you buy model, where you might get access to software for free, temporarily or with limited features. If you like what you see, you can upgrade to the full version, like subscribing to a premium streaming service. Types of paid software licensing. On the paid side, licenses can range from individual users to large enterprises. Per central processing unit, CPU, licensing depends on the number of CPUs or their core counts for a server. Per seat, charges are based on the number of individual users. Concurrent users, a license that tracks how many users access the software at a specific time. Utilization, pricing is based on metrics like CPU usage or active users. Per workstation, charge per connected workstation rather than users. Enterprise licensing, a large-scale solution that allows an organization unlimited use of software, often with some restrictions. Stay on the right side of licensing. To avoid violations, organizations must proactively manage licensing through rigorous tracking, auditing, and controls. This involves comparing installed software against licenses, scanning networks regularly, and restricting installations by unauthorized users. Proactive measures include software asset management processes, centralized distribution systems, or even locking down USB ports to prevent unlicensed software from sneaking onto company devices. Equally important is having users sign policies that clearly spell out installation rules and compliance expectations. 7. Source code management, protecting the blueprint of software. When it comes to software, the source code is akin to the DNA of a program. It dictates how it works. For businesses, this precious intellectual property must be rigorously protected. Organizations control access to source code differently based on how the software is used. Packaged software. Sometimes a company might negotiate partial source code access to customize certain features. Bespoke software. For in-house or custom-developed software, the company usually retains full access to source code. Escrow agreements. Imagine a fail-safe key handed to a trusted third party. If something happens to the vendor, the escrow enables access to the source code. Beyond security, version control systems, VCS, such as Git, come into play for effective source code management. They allow programmers to track changes, collaborate without conflicts, and revert to earlier versions if needed. 8. Capacity management. Planning for the future. Capacity management might sound dry, but it's the silent mastermind ensuring that IT systems grow alongside business needs, smoothly and cost effectively. It monitors every resource under the IT umbrella, from CPUs and memory to bandwidth and storage. The capacity planning process involves defining current and future resource needs, analyzing trends, and using modeling tools to forecast requirements. Consider this approach as trying to ensure that your team has just the right number of seats at the table for both current projects and anticipated growth. From the practical functions of utility programs to the strategic roles of licensing, source code management, and capacity planning, each of these topics works together to keep IT systems thriving. By understanding each pillar independently and reinforcing them with proper controls, systems can stand resiliently and function at their best. What stands out in IT is this: every element counts and every role matters. By managing these pieces appropriately, businesses can ensure that their systems stay productive, efficient, and ready for the future. Thank you for watching, and as always, continue learning. Stay curious, and we'll see you next video.